I know that the date here says fall 2018. I forgot to change it before I loaded the slides, and the slides are saved as images on the video recording software. So we'll just pretend that it's not there and just deal with it. Also, between class Friday and Saturday morning, I got sick, so I have a cold. So I apologize, but I'm going to sound congested on this video. And if it sounds like I stop and start the audio a lot, it's because I had a coughing fit and I had to rewind to deal with that, or so that you wouldn't have to deal with listening to that. Now, at any rate, we are covering Appendix 3, which is on pseudocode, and Section 3.1, which is on algorithms. Now, these two sections are the last two we're going to cover before the first test. And I very strongly encourage you to actually read through these sections in the book, both of them, to get a little bit more broad perspective about both of these topics. Okay, Appendix 3, pseudocode. So what pseudocode is, it is an intermediate step between English language and actual programming language, which are high-level instructions. So it's a way to... Suppose I tell you that I want you to write a program that will take as input a list of integers and will output the maximum integer in that list. And you could explain to me the way that you want to do that. You might say, oh, well, I'll compare the first integer in the list with the second one, keep the biggest one, compare the biggest one of those with the third one, keep the biggest one, and so on and so forth. That's explaining something in English language. Now, to actually turn that into an algorithm that you would put in Java or something, you have to write it in code. That's what it means by high-level instructions. Pseudocode is an intermediary step between English language and actual programming language. And ideally, pseudocode is generic enough that you'll be able to implement it on any programming language you want, like Java that you learn in your fundamentals class, or something like Python or whatever. So that's what pseudocode is. And there are different conventions used in pseudocode, and we're just going to pick one and stick with it for this section. So starting out, every pseudocode starts out with giving a procedure statement. The procedure statement gives you three things. It names the algorithm, it lists the input variables, and then typically it's going to describe what each variable input is. So here are some examples. We might have a procedure, and we're going to name the algorithm maximum. So the procedure, the name of the algorithm is maximum. It takes as input L, and then we're describing what L is. L is just a list of integers. And so this is the convention that we're going to use in here. We'll have procedure, and then italicized maximum, then parentheses, and then we have our inputs, and then a colon, and then we have an explanation of what the input is, and then we close our parentheses. Another example, procedure is going to be alpha sort, and it takes as input S, which is a list of strings. Or we could have a procedure called print hello world. It doesn't take any inputs at all. It's just going to be that hello world thing that you learn most of the time when you start programming. All right. When you're doing pseudocode, a lot of times you will make assignments. That's when you assign what a variable is. So an assignment, you have the variable written on the left, the value is written on the right, and simple English is okay when you're doing pseudocode. Okay. So for example, here's an assignment. I'm going to take a variable called x, and I'm going to assign it the value 5 by using colon equals. That's how we make an assignment. So x is assigned the value 5. Y is assigned the value x. Now this is okay because x has already been assigned, so this is a perfectly well-defined statement. And then I'll define m is going to be the largest integer in L, where L is some previously given list. Now look right here. I have in curly brackets some English. It says m will be the maximum of the list. That's what's known as a comment. And a comment is just a statement in braces and is not executed. Simple English is okay. So here's that example. M will be the maximum of L. Comments are extremely important. I can't tell you how many times I've been doing some programming and went back and visited a little bit later, and I had no idea what was going on. And it would have been quicker just to start from scratch because I forgot to use proper comments. And it's even more important when you know other people are going to be looking at your code. So use comments freely. I'm sure that all of your programming professors tell you the same thing. But this is how we use comments in pseudocode. You just put them in these curly braces. All right, our first type of construction that we'll be using in pseudocode. So we have what are called conditional constructions, and this is simply an if-then statement. So you have if, and then your condition, then, and you have your statement. For example, if input is equal to you're happy and you know it, then print clap your hands. Okay, that's a very simple conditional construction. You have your if, and then the condition that is checked, and then if that condition is satisfied, then it prints out clap your hands. So if input equals you're happy and you know it, if that fails, if that is not the input, then this part is not executed. This is only executed if the input is you're happy and you know it. Then it's going to print out clap your hands. If you want several things to happen, not just one thing like print clap your hands, if you want a couple things to happen for your statement here, then you can write it like this: if condition, then there's the command word then, and then you just have a block of statements that are indented a little bit. So if input is you're happy and you know it, then, and I'm going to come down and indent over print your face will show it, come down a new line, print clap your hands. So if you have a couple things that have to run, that you want to run if your condition is satisfied, then you just come down and you print them off right there. All right, what if you're in the situation where, if a condition is satisfied, then you do something, but if the condition is not satisfied, then you want to do something different. Well, that's where we use else. Okay, so here's an example. If condition, then statement 1, else run statement 2. Now, this means that if your condition is not satisfied, it skips this one and it always runs down to this one. Okay? If you use an else statement, this is what will always happen if your condition is not satisfied. So, for example, suppose you're making some kind of simple game where, so look at that red cursor on the screen. If you hit the input key right, then this will move to the right. Else, it will move to the left. So when this conditional construction is executed, this character will always be moving, and it will move to the right if you hit the right key on your keyboard. And if you hit any other key, then it will move to the left. So using an else means if this condition isn't satisfied, it moves on to this one and it executes it. What if you don't want that to happen? Well, you can use an else if construction. So here's how this works. If condition 1, then run statement 1. Else if condition 2, then run statement 2. Else run whatever we're going to call statement. So here's an example. If your input key is up, then move the character up. Else if input key is down, then move the character down. Else if input key is right, then move the character right. Else if input character is left, move the character left. Else print, huh? So this would be if you're playing some type of two-dimensional scroller game, like a really simple snake game or something. So here's the cursor. If you hit the right key, it moves right. If you hit let's start right here at up. If you hit the up key, it goes up. If you hit the down key, it goes down. If you hit the right key, it goes right. If you hit the left key, it goes left. If you hit any other key, then it's going to print out, huh? Because it's expecting you to tell the cursor how to move. All right, loop constructions. This is when you want to have something happen over and over and over until a certain condition is satisfied. So the first one we're looking at is for. So for your variable equaling an initial value to a final value, execute a block of statements. So for example, we start out by assigning this variable sum to be 0. So I assign sum to be 0, and I have my loop construction. For I going from 1 to 10. So I is going to take on the values 1 to 10. Sum is going to be redefined as sum plus 1. So let's see how that would work over here. Start out with sum equals 0. And then I'm going to run this for construction. I is going to go from 1 to 10. So when I is equal to 1, sum is going to get redefined to be the previous value of sum, which was 0, plus the current value of I, which is 1. So I get 1. And then when I is equal to 2, because remember I'm running all the values for I from 1 to 10. Okay, for I going from 1 to 10, I'm going to execute this. So when I is equal to 2, sum is going to be defined to be the previous value of sum, which was a 1, plus the current value of I, which is 2, so I get 3. Then when I is equal to 3, sum is going to be defined to be the previous value of sum, which was 3, plus the current value of I, which is 3, and you get 6, and so on and so forth. And you're going to stop. The last one you'll execute is when I is equal to 10. Okay. All right. So it'd be a nice exercise for you to go ahead and work all of this out in detail and see what the final value of sum would be. That would be a good little exercise to practice. All right, another way to do a loop construction is use while. So while a condition is satisfied, run a block of statements. Okay. So here's an example. We'll define the variable x to be 1, and then while x is less than 9, I'm going to redefine x to be 2 times x. So let's see how this example would work. So I'll start out with x is defined to be 1. So I want to check, is x less than 9? Yes, it is, because x is equal to 1. So I redefine x to be 2 times 1, or 2. Now I check again, is x equals 2 less than 9? Yes, it is. So I redefine x to be 2 times 2, which is 4. So check again, going back to the while loop, check again. Is x equal 4 less than 9? Yes, it is. So keep going. So redefine x to be 2 times 4, which is 8. And then x equals 8 is less than 9. Check. So redefine x to be 2 times 8, which is 16. So check again. Is x equals 16 less than 9? No. That looks, I can't use an x because it looks like I'm saying x. So why don't we make that, we'll just say no. So since 16 is not less than 9, that means we exit the loop, and the final value of x is equal to 16. Okay. So what do we do here? We just followed the loop. Every time something was done to x, every time it was multiplied by 2, then we go back and we check and see if the condition for the while loop is still satisfied. If it is satisfied, then we're still in the while loop. And as soon as we got over here to x equals 16 and made that check, that's when we jump out of the loop and then we're done. And we end up with the final value of x as 16. Okay, return statements are important. I have a horror story that I won't give you all the details for, but when I was in graduate school, part of my dissertation was writing an algorithm to check a bunch of things for this pure math project, and one of them ran for 7 days straight. And the way I had it set up, I could check to see if the process was running, but I couldn't see anything that was going on. And at the end, when the process stopped, I had forgotten to tell my program to return the output that it calculated. So I lost, that whole week and a half of time, and I had to start it over and fix it. So that was a lesson learned. So always make sure you return, you include a return whenever it's necessary. But all this does, it just shows how a procedure returns an output. So for example, procedure is called mystery. The input is x, which is an integer. So the algorithm is going to be I is assigned to be 1. As long as I is less than x, redefine I to be I times I plus 1, and then it's going to return I. Okay, so basically you're going to pick a mystery integer, and this while loop is going to do this arithmetic operations on it, trying to identify what the mystery integer was, and then it's going to spit out I once it finds it. And again, this would be a nice one for you to kind of play around with. Pick out an integer, and then run this through and see what happens, and see what the return would be and how it compares to the actual integer you picked. So play around with that. All right, section 3.1, algorithms. Please do not say the word logarithm. That's a totally different concept. An algorithm is a finite sequence of precise instructions for performing a computation or for solving a problem. Basically, it is just some instructions to do something. But you've got to be careful because it's finite, a finite number of instructions, and they're precise. You know exactly what to do when you see the algorithm, and it's for solving a problem. So here's our first example of an algorithm, finding the maximum element in a finite sequence. So the procedure is called max, and it takes as its input n integers. Now, this is something that I want you to pay attention to, so kind of key in right here. How do you know that there are n integers there? Well, you have these little subscripts. These are called your indices. Okay, so this A1 has a subscript 1, so this is at the very first place in the list. This has a subscript 2, so it's the second entry in the list. And we go up to n, so this is the nth entry in the list. That's important because when you're writing algorithms, the number of elements in the list are going to pop up frequently, like right here. So it takes this list of n integers. We're being told that they're integers. So the algorithm assigns max as a variable now, not as a procedure name, but as a variable. Max is defined to be the first entry in the list, A1. And then for I, going from 2 to n, so I is going to run from this index 2 to the last index. So from the second place to the nth place, we have this conditional running. If the current value of max is smaller than whatever AI is, then max is assigned to be AI. So basically this algorithm compares the first integer with the second integer. Okay. Well, first of all, it assigns max to be the first integer. Then it compares the first integer with the second integer. And if the current value of max is less than what it's compared to, then max is reassigned. So it compares all of these integers together one by one, or it compares whichever one it thinks the maximum is one by one, going down the list until it gets to the last one. And it has to go through every single one of them. This algorithm does. And then it returns whatever the current value of max is. And max is the largest element. Okay. Now, I had thought about whether I should do lots of examples of running these, showing you how they work. And I decided not to, because I think it would be to your benefit to kind of fight through these. But most of the time, just to go through these yourself and try to work out how they work. I am going to do one. I am going to do this one, but this is probably the only one that I'm going to do, so you can see how this works. So why don't we take I'm going to use red because red will show up if I have to run down over where this slide is. So I'm going to run max of, so I need a couple integers. I'm just going to do 3 so it won't be that long. I'll take -1. No, I'll tell you what. Why don't I take 0, -1, and 2. Okay, I'm going to run this max algorithm on this list, 0, -1, and 2. So I'm just going to go through the algorithm. It starts out by max being defined to be the first entry in my list. So start out, max is defined to be 0. Okay? Then the for loop starts. Okay? The for loop. So as I goes from 2 to n, so for my example, my n is equal to 3 because I have 1, 2, 3 elements in my list. So as I goes from 2 to 3, I'm going to check this conditional statement. So how does that work? Well, it works like this. So when I is equal to 2, if my current value of max is less than A2, then I'm going to reassign max to be A2. Sorry, it ran off the side of the screen. I apologize. So what happened here? So max is 0. That is less than, it is not less than A2 because A2 is -1. So since this condition is not met, this statement never gets executed. And max is still equal to 0. Nothing changed with max. So now I is going to be equal to 3. And I run if max is less than A3, then max is redefined or reassigned to be A3. Well, max is equal to 0. A3 is equal to 2. So yes, max is less than A3. So that means I'm going to execute this statement. Max is assigned to be A3. So max is now going to be 2. And now I've ran through my entire list. There's nothing left for this for to execute. Okay, so I'm going to exit out of my loop, and it's going to return max. So my algorithm is going to return max, which is equal to 2. So that's how that works. And again, I'm not going to go through these for most of them because I feel like it would be better for you all if you just fought with it on your own, because it's not complicated. You just do it step by step by step. And the first test is going to give you an algorithm where you'll have to do this. So you do it in a couple of homework problems, but it would be great to practice it with the ones on these slides too. Okay, properties of algorithms. What makes an algorithm a good algorithm? Or what makes something just an algorithm? Well, first of all, an algorithm has to have an input. Okay, an algorithm has to have an input values from a specified set. It needs to have an output. For each set of input values, an algorithm produces an output value from a specified set. The output values are the solution to the problem. Remember, the whole point of an algorithm is to solve a problem, and the outputs should be your solutions. Definiteness. The steps of the algorithm must be defined precisely. Okay, I can't have an algorithm say something like, okay, now go to the largest integer in the list, unless I've already given steps about how to find the largest integer in the list. An algorithm should be correct. I know this should go without saying, but it can't. An algorithm should produce the correct output value for each of the input values. This is where your alpha testing comes into play. When you write an algorithm, no matter how good or elegant or pretty you think it is, check it to make sure it gives you the correct value on some things that you know the answer to before you go on. Finiteness. Okay, an algorithm should produce the desired output after a finite, but perhaps large, number of steps, or another way to think of it, or length of time for any input in the set. Effectiveness must be possible to perform each step exactly and in a finite amount of time, and generality. The procedure should be applicable for all problems of the desired form, not just for a particular set of input values. That is, you wouldn't write an algorithm that could find the largest integer in the list. It would only work for the list 0, -1, and 2. All right, an algorithm that just finds the largest integer in that list. You want it to be general. It should find the largest integer in any list you give it. That's what generality means. Okay, some more algorithms. Linear search algorithms. Search algorithms are important. You use them all the time when you hit Control F on a website, or you're reading a book on a PDF and you want to find where something occurs. Well, search algorithms happen. Here's one of them. It's called linear search. It has two different inputs now. I want you to watch how this works. First of all, it has x an input, which is an integer. Now I have a comma here because I have my second input, a list, A1, A2 through AN, and these are distinct integers. Distinct means that none of them are the same. Okay, so there are two inputs here. I have my first input is x, which is an integer, and my second input is this list of distinct integers. So how does this algorithm work? This is one where I want you to try it. Try it on your own. That is, I want you to pick an integer and then a list of distinct integers and try to run this algorithm. So take I to be 1, is how it starts out, and then as long as two things are satisfied. Remember how ANDs work from our section on truth tables. An AND is only true when both parts are true. So the while loop is only going to occur when both of these are satisfied. As long as the current value of I, your index, is less than or equal to n, and n is the number of elements in this list, as long as your index is smaller than the number of elements in your list, and x, this input, is not equal to AI, then you're going to increase your index by 1. Okay? What this is saying is, it checks two things. First of all, it checks that you're not at the very end of your list. And it also checks that you haven't already found the integer you're looking for. It checks that x is not equal to a sub I. As long as you're not at the end of the list and you haven't found your integer, then it says the index increases by 1. That is, you move on to the next number. So once we get out of the while loop, we have a conditional. If I is less than or equal to n, that is, if we're at one of the places in the list, then assign the location variable to be I. Otherwise, it's going to return 0. So what that's saying is, if we're able to find x in this list, it's going to assign location to be the place where we found it. Otherwise, location is assigned the value 0. And the algorithm returns location. So location is the subscript of the term that equals x, or it's going to be 0 if x is not found. Now again, I want you to try this. If it seems confusing, it won't be once you work out a couple of examples. Here's a more efficient search algorithm than going through each thing step by step by step, and it's called the binary search algorithm. And let's talk about it briefly. Before I do, look down here at the bottom at these two bullet points. It says, note that A1 is less than A2, ... is less than AN. That's saying that this list of integers that you input, they're all increasing. That means the first one is smaller, and the second one is smaller, and the third one is smaller than the last one. And finally, I want you to look at this right here. This is what's called the floor function. And here's the definition of it. The floor function drops any non-zero decimal. So that is, the floor function works like this. If you want to find the floor of, say, 3.1, it drops what comes after the decimal, so that's just equal to 3. The floor of 8.929, that's still just going to be 8. Okay, so it's not rounding anything. It's literally just dropping off all of the part that comes after the decimal point. The floor of 7, well, that's just 7 because there's nothing to drop off. Okay, that's what the floor function does. All right, so let's talk through this algorithm. And again, I'm going to encourage you to try to work this one out on your own. This one will be a little more tricky. So start with just a small list. Procedure is called binary search. It takes 2 different inputs, x, which is an integer, and it takes a1 through an, which are increasing integers. So you do this example, pick an integer, and then pick a list of start with like 4 integers to search for, and then do another one with 5, and see what difference it makes if you have an odd number or an even number. So it's going to define 2 different index variables. I is assigned to 1, so it's going to be able to grab onto the first one on the list, and j is assigned to n. It's going to grab onto the last one in this list. And it tells you what they're doing in comments. I is going to be the left endpoint of the search interval, and j is the right input of the search interval. So let's see what happens. As long as I is less than j, that is as long as I is less than j, we define m, and that comes from, because we're kind of getting the middle. M is going to be I plus j divided by 2 floor. Okay? So basically, m is going to be the middle between like it's going to grab on to like the middle number. And if that division comes out to have a decimal, the floor function drops the decimal. Okay? And then it checks. If x, the one you're searching for, is bigger than a sub m, that is the one in the middle, then we redefine I to be m plus 1. Okay? We move our I index over to be m plus 1. Otherwise, we're going to move j to be m. Now this takes advantage of the fact that these are increasing integers. Okay? These are increasing integers. Because if our x, one we're looking for, is bigger than am, then we're going to move over a little bit, past the middle one. Because if I is bigger, it has to be over here on this left-hand side of integers, because, again, they're increasing. And if we don't get that it's bigger, then j is going. Then our search interval is going to move over to the middle one. J is going to be moving over to here, and we're looking at these smaller ones here on the left side. Okay. So we keep doing that until I is no longer smaller than j. Then we exit the while loop. And then if we found our integer, if x is equal to ai, then we're going to assign location to be I. Otherwise, assign location to be 0. And again, we return location. Location is the subscript of the term ai that we're looking for. Otherwise, it's going to be 0 if x is not found in the list. This is not as complicated as it looks. Try some examples on your own. Sorting algorithms. So these are really interesting. And you'll notice that there's a YouTube link right there, and I'm going to show you that a video in just a second. I'm going to inception this and show you a YouTube video inside a YouTube video. The PowerPoints that are on D2L, this is a clickable link, but I'm also going to put this link and one more in the comments under this video. Excuse me, in the description under this video, so you can click directly to it. But sorting algorithms are when you want to put numbers in increasing order. From smallest to largest. If you've ever used an Excel file, maybe it's been necessary to sort something. So this procedure, this one is called bubble sort. And it takes as input real numbers. Okay, now not just integers, it takes real numbers as inputs. And the only condition we have on that is I need to have more than one of them, or else the algorithm will fail. Okay, so what it does, for I equals 1 to n minus 1, okay, I is going to start at 1, and it's going to run through n minus 1. So I is going to run from the first one to this one before the last one. I'm also going to define a second loop construction with 4. And then for j equal to 1 to n minus I. So for every value of I, okay, there's going to be a value of j assigned. And if aj is bigger than aj plus 1, then I swap them out. And that's all the algorithm does. Okay, it just swaps them out. So let's see how this works. This is a folk dance, a European folk dance demonstrating the bubble sort algorithm. And I'm not sure how volume works, how the volume mixing works. So there's a chance this may be really loud. If so, get your finger on the volume button to turn it down if it blasts your ears. I don't think it will though. But let's see how this folk dance works. I think the volume's okay. So here are the indices for our numbers, and look, they're being compared one by one. And since 3 is already smaller than 8, those two didn't interchange. But these two did because 7 is smaller than 8. And it keeps comparing pair by pair all the way up. So notice there's already a problem right here. It didn't catch this one. 7 is not smaller than 2, so the algorithm will have to work some more. And those two didn't switch, so they did that spinny move. Right. Now these two are done. They won't get compared anymore. They stop. But it starts all over from the beginning. And so this one's done. She won't get compared to one anymore. But we start over with these two, and these two, they're good. Oh, we have a switch right here. So we get to watch the guy slap his feet when he walks backwards. No, they're good. Now I think we're going to be done. It's going to end quick now. Those two are good. Those two are good. 2 more comparisons. Now watch. Even though the algorithm actually accomplished the job, it doesn't know yet until it has to go through all of them and check that time. And so it's done, and then we can watch them dance because it'd be rude not to let them do their thing. Okay, let's just abruptly skip to the next one. And skip. Okay, that was fun. So that bubble sort algorithm, you can see that it gets the job done, but it's not super efficient. It had to go through and check each pair, and even though the order was done near the end, it still had to go through and check them again. And it had to check all the way through one by one every single time. Here's a different sort algorithm called the insertion sort. Insertion sort. That's hard to say for me anytime, much less when I have a cold. That is more efficient than the other one. So let's talk through this, and then we have another awesome video to watch. That is more folk dancing. So the algorithm is called insertion sort. It takes as input a list of n real numbers where there's at least 2 of them. And now I define an index j that goes from 2 to n. So j is going to start here, and it's going to go through to n. And when j is defined, I is going to start at 1. And as long as ij is bigger than ai, I increase the I index by 1. Then m is defined to be aj once I get out of the while loop. And then for k equals 0 to j minus I minus 1, a j minus k is defined to be aj minus k minus 1. And then at the end, ai is defined to be m. And that actually does it, right? This looks like it makes no sense whatsoever. I really want you to try this. Try to do this. But first, let's watch a video that demonstrates how this algorithm works. And it would be maybe a good idea to try it with these numbers that are on this video and see if you can follow each step on your own. Okay, here we go. Now notice what happened when those two got sorted. These two got compared with the one before, and since there was no switch, it moved on to the next one. So smaller ones keep getting moved further and further down. And because that happens, once this order is established, these guys are already done. See, and there's no more comparing these ones down here because we already know that this one is bigger than this one, is bigger than this one, is bigger than this one. And so that's it. See how much faster that was? So this is an example of where 2 algorithms can do the same thing, but one of them is much more efficient than the other one. Let's just abruptly skip this one too. Okay. So like I said, we had those two different sort algorithms, and one of them ended up being a lot more efficient than the other one. And that's going to come into play a lot as you learn more and more programming. You'll find out that there may be more than one way to do something, so we want to look for the more efficient one. We actually have a whole section on that later on algorithm efficiency. So that is the end. We're done. So like I said, try these algorithms out on your own, especially those last 3. Try working them out with some concrete examples. And if you can do that, then you'll have a really good understanding of this. All right, that's it. I'll see you in class.